Today's video lesson is about the ideal gas law. It's a quantitative way to describe gases that lets us calculate pressure, volume, temperature, or amount of gas, provided that you have three of the four variables. We're going to build the ideal gas law based upon what you learned in the gas simulation. We're going to go back to the idea of direct and inverse proportionality and look a little more carefully at each of the characteristics. The first characteristic we're going to look at is amount of gas and pressure. You learned that the pressure is directly proportional to the amount of gas in the container. This little sign right here is the Greek letter alpha, and it's the proportionality sign. So this little blue sentence reads, pressure is directly proportional to amount of gas. In the ideal gas law, the amount of gas is going to be represented by the lowercase letter n. The reason for this is that amount of gas is expressed in terms of number of moles of gas. So you can think of that little n as representing number. As you've probably figured out, the reason that the pressure is directly proportional to the amount of gas is that more particles in the container equal more collisions with the walls. And as you can remember from earlier in your notes, the pressure exerted by a gas is caused by the particles hitting the walls of the container. Next, we'll look at temperature and pressure. You also found out in the gas simulation that the pressure is directly proportional to the temperature. And from watching the particles move around in the tank, you probably noticed that as the particles move faster, they hit the wall more often, and each collision with the wall is harder. Therefore, each individual collision exerts more force against the wall of the container. And lastly, you have learned that volume and pressure are inversely proportional to one another. So to write that, we would say that pressure is proportional to the inverse or the reciprocal of the volume. And this is because when you make your container smaller, the particles are more confined, and as a result, they hit the wall more often. So if you keep your amount of gas constant and decrease the size of your container, the pressure inside the container is going to go up as the gas particles are pushed closer together. The ideal gas law is built by taking all of these things and putting them together. As we put all of these things together, we come up with pressure is proportional to the amount of gas times the temperature divided by the volume. Now, proportionality isn't particularly useful if we need to make a mathematical calculation. So in our next move, we're going to take away the proportionality sign and replace it with an equal sign and a proportionality constant. A proportionality constant is just a constant number that allows you to replace that proportionality sign with an equal sign. The numeric value of the proportionality constant depends upon the situation. It happens in this particular situation that scientists have figured out that the proportionality constant needed for the ideal gas situation is 0.08206 liters times atmospheres per moles Kelvin. This set of units will remain on R at all times, and R is called the ideal gas constant. This number, along with its units, will be provided for you on your test. Scientists use this, which is called the ideal gas law, in a slightly rearranged form that's a little bit easier to remember. The common format for the ideal gas law is PV equals nRT. This is an equation you're going to have memorized, but you will always be given the value for R. Because of the units on R, there are some limitations to using the ideal gas law. The limitations are that pressure must be in units of atmospheres. You may have to use the conversion factors on page 21 of your notes if the pressure is given to you in some other units. Those conversion factors will be provided for you on a test as well. The volume must be in units of liters. Occasionally the volume is given in milliliters, and you can use the conversion 1,000 milliliters per liter to get your volume into liters. N, or the number of moles of gas or the amount of gas, is going to have to be expressed in moles. You might have to use your periodic table to convert grams to moles. R is the ideal gas constant. By nature of being a constant, it's always going to be the same, with a value of 0.08206 liter atmospheres per mole Kelvin. And temperature must be in Kelvin. You will have to use the equation at the bottom of page 22 to convert from Celsius to Kelvin. Occasionally, your temperature and pressure will be given to you in the format of standard temperature and pressure. The problem may say, this happens at standard temperature and pressure, or STP. You'll need to know that standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere. Both of these values are exact values and have infinitely many significant figures. Here's an example of using the ideal gas law to solve a problem. This is similar to the 3 problems that you're going to solve in your ideal gas law homework. The first hydrogen balloon flight required 2,600 grams of hydrogen at a temperature of 23 degrees Celsius and a pressure of 750 millimeters of mercury. What was the volume of this balloon? Now, I kind of expect a relatively large answer here because this is a balloon flight that lifted a person off the ground. So we expect kind of a big answer. My problem here is that I need to find the volume. I'm going to take a quick read through the problem and gather all of the information. So reading through the problem, we find out that the pressure is 750 millimeters of mercury. We don't know the volume. The amount of gas is given in grams, 2,600 grams of H2. Remember that hydrogen is diatomic. R, or the ideal gas constant, always stays the same, 0.08206 liter atmospheres per mole Kelvin, and the temperature is 23 degrees Celsius. We're going to need to use the equation PV equals nRT because that's really the only thing we know about gases at this point in time. Remembering our limitations, we're going to have to make some conversions here. Based upon the ideal gas constant, our answer will come out in liters. We need to put our pressure in terms of atmospheres, our amount of gas in terms of moles, and our temperature in terms of Kelvin. I'm going to do all the conversions right here in the information step. My 750 millimeters of mercury, I can multiply by 1 atmosphere over 760 millimeters of mercury. I have to round that to 2 significant figures. I get 0.99 atmospheres. I don't know my volume, but it will come out in units of liters when everything is done. My amount of gas needs to be expressed in moles. 1 mole of H2 has a mass of 2.01588 grams of H2, or 1,300 moles of hydrogen. Ideal gas constant is always the same. And to convert my temperature between Celsius and Kelvin, I have to add 273.15, coming up with an answer of 296 Kelvin. I had to round that to the ones place because my original temperature was only given to the ones place. Now I'm going to take all of these converted values. I'm going to plug them into the ideal gas law. Here's my pressure times my volume is equal to my number of moles times the ideal gas constant times my temperature. Notice that I took the time to write units on every single one of these numbers. I expect when you're solving ideal gas problems that you will take the time to write units on all of your numbers as well. This does a final check to make sure that the pressure units of atmospheres match atmospheres on the ideal gas constant, that your amount of gas is given in moles to match moles on the ideal gas constant, that your temperature is given in Kelvin to match your Kelvin on the ideal gas constant, and that you're aware that volume will come out of this with units of liters. After doing all the algebra, you'll find out that you have a final volume here of 3.1 times 10 to the 4th liters, limited to 2 significant figures by both the atmospheric pressure and by the fact that my amount of gas only had 2 significant figures to start with. The final thought for today related to ideal gases and the ideal gas law is that if you were to use the ideal gas law and plug in standard temperature and pressure and 1 mole of gas and solve for the volume, you would find out that 1 mole of gas occupies 22.4 liters at standard temperature and pressure. It doesn't matter which gas you have, because from the perspective of the ideal gas law, all gases behave the same. This is a shortcut that can occasionally be used as long as you have 0 degrees Celsius, 1 atmosphere of pressure, and exactly 1 mole of gas.